Hello everybody, and welcome to our first video on Calculus 1. So, we're going to start with the topic of limits. And for this first lecture video, what we're going to deal with is just the intuitive definition and how to interpret graphs of functions and determine limits from those graphs. So, this definition that we're going to use for now is a very informal definition. It's good enough to get the idea of what the limit is, but it's not powerful enough to use for more complex problems. So for now, we're just going to deal with a simpler definition, build up our sort of intuitive understanding of how limits work, and then we'll deal with some more complex things after this. So, the informal definition of the limit. We say that the limit as x approaches c of f of x equals L, or in other words, the limit of f of x as x approaches c is L, if the output values of the function f of x get arbitrarily close to L when the input x is sufficiently close to c. So again, another way to say this is when the input x gets close to c, then the output y gets close to L. So what we're going to do first is just look at a function, f of x equals x minus 2 over x squared minus 4. And we're going to make an educated guess of the value for the limit as x approaches 2 of the function. And we're going to do this by drawing a table. Now, I want to be clear, this is not a rigorous approach to evaluating limits, and this is not an approach you will use in the future. This is just something we're going to take a look at to help build our intuition, because for trickier problems and functions with more unusual behavior, this approach can actually lead you to the wrong answer. So let's just make sure that that's super clear. All right, so we're going to draw a little table. So this row will be our x values. This will be our y values. And at the center, we'll have x equals 2. But of course, this function is undefined for x equals 2 because when you plug in 2, in the denominator, get 2 squared is 4, minus 4 is 0, and we can't divide by 0. So this is undefined. So what the limit is asking is, well, okay, this function is undefined at 2, but what's happening when x gets really close to 2? So, okay, let's go ahead and look at a couple values on either side here. So I'm going to work with fractions. You don't have to do that for this kind of problem. You could definitely work with decimals. But we're going to be using a lot of fractions in this course, and so I figure might as well practice early rather than wait until we really need them. So I'm going to pick numbers that are very close to 2, but a little bit less than 2, and kind of see what's happening from each direction. So I'll start with 1.5, or in other words, 3 halves for my x value. And then 1 3/4, which is 7/4. And then 1 7/8, which is 15/8. And then we'll just go out by the same intervals on the other side. So 2 is 16/8, so this will be 17/8. And then 9/4. And then 5 halves. And so all we're going to do here is just plug each of these x values into the function and take a look at what's happening as we get close to 2 from each direction. Okay, so let's take a look at f of 3/4, or sorry, 3 halves, I meant to say. So that's 3 halves minus 2 over 3 halves squared minus 4 equals, well, 3 halves minus 2, 2 is 4 halves, so that's negative 1/2. Divided by 9/4 minus 4. But of course 4 is the same thing as 16 over 4. So this is negative 1/2 divided by negative 7/4. And so when I multiply by the reciprocal, I end up with 4 over 2 is 2. The negatives cancel, so I get 2/7. Now, I'm going to start skipping some of the little steps here in between, just to save a little bit of time. All right, so let's take a look at f of 7/4. So 7/4 minus 2 is -1/4. 7/4 squared is 49/16 minus 4, which is 64/16. That makes -1/4 over. Okay, that's going to be -15/16. Multiply by the reciprocal, the negatives cancel. 16/4 is 4. I get 4/15 here. Okay, let's do the rest of these here. F of 15/8. Okay, 15/8 minus 2, going to be -1/8 divided by 15/8 squared. So 15 squared is 225 over 8 squared, that's 64, minus, and 4 is the same thing as 256 divided by 64. So this is -1/8 divided by -31/64. And again, I multiply by the reciprocal here. 64 divided by 8 is 8. The negatives cancel. I get left with 8/31. Okay, now we go over 17/8. So then we need 17 minus 17/8 minus 2, which is a positive 1/8. And then we're going to need 17 squared. So that's going to be 289 divided by 8 squared. That's 64. Minus 256 divided by 64. Again, I'm just rewriting the number 4 with the denominator 64. That's 1/8 divided by. That's going to be 33/64. Okay, multiply by the reciprocal. 64 divided by 8 is 8. I get left with 8/33. Almost done. Okay, f of 9/4. 9/4 minus 2 is 1/4. 9/4 squared is 81/16. And 4 is the same thing as 64/16. That's 1/4 over 17/16. Multiply by the reciprocal. 16/4 is 4 divided by 17. All right, and finally, I just realized I miscopied 4/15 from earlier. That's 4/5. Yeah, that should have been 4/15. Thought that didn't look right. Okay, last one. F of 5/2. All right, 5/2 minus 2 is 1/2 divided by 5/2 squared. That's 25/4 minus 4, which is 16/4. That's 1/2 divided by 9/4. Multiply by the reciprocal, and I get 2/9. Now, I could convert all of these to decimals and then determine, hey, what decimal does it look like it's approaching? But actually, this function I chose to be pretty nice. It's pretty convenient. So we can actually kind of just figure it out by looking at the fractions that we have involved here. So notice 2 is in between each of these pairs of numbers. And 8/31 and 8/33, hey, what's right in between that? 8/32, which is 1/4. And 4/15 and 4/17 here, what's right in between that? 4/16, that's also 1/4. And 2/9 and 2/7, 2/8 is between that, that's 1/4. So my guess is that this limit is 1/4. Meaning that as I take these x values closer to 2, the value that's being approached in the middle is 1/4. Okay, so that was a little bit of a long way to handle that, but it made sure we got our fraction practice in. We won't have to do any more of that for this video. Okay, so now let's get to the big picture stuff with graphs. Now, I do want to point out again, plugging in values like this is, of course, not practical. and not an efficient or effective way to evaluate limits. That's why we're using the term guess here, because I can have functions that behave pretty extremely near the point, and even though the numbers might look like they're approaching something, maybe I just haven't chosen numbers close enough to 2 yet. Maybe the function has some really sharp turn in it. So to illustrate what I mean is, we might have a function whose graph goes like this really sharply near whatever point you're looking at, let's say 2. And if I was plugging in a bunch of values here, if I just plugged in 3 values on either side, I'm not going to get the limit correct, because I'm going to think that the limit, the y value, is somewhere around here. But that would be wrong, because the limit is actually up here. So again, this is not a rigorous approach. I just want you all to see the basic idea of what's going on, that as your x values get closer to the place where you are taking the limit, the y value gets closer to this value L, we call it, or 1/4 in this case. Okay, so again, back to the graphs. Definition, the left-handed limit. We say that the limit as x approaches c from the left of f of x equals L if the output values of the function f of x get arbitrarily close to L when the input x is sufficiently close to, but less than c. So we'll look at a picture here in a moment, some examples to make sure that that's clear. And the right-handed limit says, we say that the limit as x approaches c from the right of f of x equals L if the output values of the function get arbitrarily close to L when the input x is sufficiently close to but greater than c. So let's go ahead and tackle that in this next example. We'll look at the left-hand limit as x approaches, that should be 5, of this function. So what that means is we're looking at 5 and we're starting to the left of it, because we're looking at what's happening to the function for values less than c, right? That's the left-hand limit. Values less than c. So the way to deal with this is just draw a little arrow tracing along the graph towards 5 from the left. And what y value do I approach? Oh, that's just 1 there, so this limit is 1. That's it. There's nothing else to it. Now if we take the limit as x approaches 5 from the right, and we try to determine this from the graph, we go to the right of 5, that is values greater than c, c in this case is 5, and we just draw a little arrow tracing along the graph. And which y value are we approaching? Oh, we're approaching 3, so we would say the limit from the right is 3. And that's it for example 2 here. So now, what do we mean when we say a limit exists? We mean that the limit from the left and the right-hand side are equal. So this is our theorem. If the limit as x approaches c from the left of f of x equals L, and the limit from the right of c of f of x equals L, then we say that the limit as x approaches c of f of x exists and is equal to L. In other words, we just write the limit as x approaches c of f of x equals L. So let's take a look at example 3 here. Now this particular theorem goes in both directions. So if the left and right hand limit are not equal, we actually do also mean to say that the limit does not exist. So let's just go through these examples and work that out. So if I take the limit as x approaches c from the left here, we trace along the graph, and we get, oh, that's approaching 1. And we take the limit as x approaches c from the right of f of x here. What does that equal? Oh, well, that's approaching 3. Well, these two are not equal, so this implies that the limit does not exist. So when we say that the limit exists, what we mean is that we are approaching the same value from the left and right, from an intuitive standpoint. That's what we mean. We're approaching the same number from both sides. So we say that this limit does not exist. Okay, moving on. All right, now for this next example, we'll do the same thing. We'll take the limit as x approaches c from the left of the function. We will trace along the graph, and we say, oh, the y value that I'm approaching from the left, hey, what is that? That's 2. And when I take the limit as x approaches c from the right, oh, what's that? Oh, it's also approaching the y value of 2. So these two things are equal. So that implies that the limit exists, and we say that this limit equals 2. All right, now, in this case, this third example here, we're going to take a look at the limit as x approaches c from the right first, because that's going to actually let us stop very quickly. So this limit does not exist. What we mean when we say a limit exists is that it approaches a fixed finite number, and this left-hand limit is growing unbounded. That's what we mean here when we've drawn this asymptote, and it indicates that this limit is going up. And if that limit doesn't exist, then certainly it can't be equal to the left-hand limit. So it's immediately, as soon as we know that one of our sided limits does not exist, we can immediately conclude that the limit itself at c does not exist. All right, well, let's move on a little bit further. So now we're going to take a look at this graph, and we're going to interpret the graph to find all of the following values. And we're going to kind of do this a little bit quickly here. So the limit as x approaches 2 from the left. Find 2. Go from the left, draw your little arrow. What y value are you approaching? Oh, that looks like 1, so this is 1. Okay, now the limit as x approaches 2 from the right, so I find 2 again, but this time I start to the right of 2, just a little bit, and draw my arrow. And here I'm approaching 4. Now, f of 2 is the actual value of the function. Now, if we have an unbroken line, the value of the function is wherever that curve is. But when we have breaks in the curve, we indicate the actual value by placing a filled-in dot. So when I look at f of 2 here, x is 2. What's my y value? That's 3. All right, now we look at the limit as x approaches 2 of f of x. And what's our conclusion? Well, the left and right hand limit are not equal, so this does not exist. Now we look at the limit as x approaches 4 from the left. So 1, 2, 3, 4. So that's here. So we trace from the left, and the y value we're approaching is 1, 2, 3, 4, 5. This limit is 5. And now we'll look at the limit as x approaches 4 from the right. So I go back to x equals 4, go a little bit to the right on the curve, trace my arrow back. What y value am I getting close to? That's 1. So again, the left and right hand limit are not equal here, so the limit as x approaches 4 does not exist. Now f of 4, again, we look at x equals 4. The filled in dot indicates that that's the actual value of the function here, and that y value is 5. Now we look at the limit as x approaches -4 from the left. So 1, 2, 3, 4. And we're approaching from the left. My y value is 3. So this is 3. And the limit as x approaches -4 from the right. I go to -4. I go a little bit to the right. I trace towards -4. And that's going to be also 3. So although I did not include it in the list to solve, that means that the limit as x approaches -4 of f of x equals 3, since both the left and right hand limit are equal. All right, that's it for that one. We've interpreted that graph. Now let's take a look at this last question. Draw the graph of a function that satisfies the following conditions. F of 1 is 2, the limit as x approaches 1 of f of x equals 3. The limit as x approaches 2 from the left of f of x equals -1. The limit as x approaches 2 from the right of f of x equals 0. F of 2 equals 2. The limit as x approaches -1 of f of x equals 1. And f of -1 equals 1. Ooh, that's a lot of information. So my recommendation with any sort of problem like this, where you're asked to take information and draw a function that satisfies it, is to only do one piece of information at a time. Draw the bare minimum you need to for each piece of information, and start with any points. So f of 1 is 2, f of 2 is 2, f of -1 is 1. If we start there, that's going to be the easiest thing to draw. So we'll just plot those points. F of 1 equals 2. When x is 1, y is 2. So I'll plot that point there and leave it. I don't need to draw anything else for now. Just draw the bare minimum I need to for each feature. Now f of 2 equals 2. So when x is 2, y should also be 2. Okay. F of -1 is 1. So when x is -1, y should be 1. All right, now let's start looking at our limits. Well, the limit when x approaches 1 of f of x is 3. That's the limit from both the left and right. We don't have a qualifier here, so that means both limits from the left and right have to be the same. So when I go to x equals 1, my y value should be approaching 3 from each side. So I need an open circle here and just a little tail off of each side. I don't have to draw more than that. And if I do, I'm very likely to make a mistake. So we have to make sure that this is a function, and a function must pass the vertical line test, right? So if I have a graph like this, that's fine. But if I have a graph like this, this does not pass the vertical line test, so it would not be a function. So in this case, you would have 2 outputs for 1 input, which violates what we want a function to be. We want a function to only give us 1 answer for each input. Okay, so again, we got to make sure we draw this carefully, because if I draw too far, I might draw something that doesn't pass the vertical line test, and then it wouldn't be a function. We just got to be a little careful. Okay, let's mark that condition off. Now the limit as x approaches 2 from the left is -1. So that means when I look at x equals 2, I need to go down to y is -1. And I should have an open circle with a little tail from the left. And now when x approaches 2 from the right, f of x should approach 0. So I should have a little tail, and a tail coming from, or the tail should be coming from the right, and it should be approaching 0. And finally, the limit as x approaches -1 of f of x is 1. So I can just go here to 1, 1, or -1, 1, I mean, and put a little tail on either side. Now we just connect the pieces together, and we make sure that when we connect them, we make a function. So don't cross over anything twice. So here for this left side, there's nothing else here, so I can do whatever I want, as long as it's still a function. And now, what's my next point from here? The next tail I have to go to is here. So I can have this just curve upwards a little bit. And now here, this tail needs to meet this. So I'll just curl this down. Make sure your line doesn't turn into a straight line. It's got to have at least a little bit of slope to it. It's a pretty sharp turn, but as long as it's not actually getting cut by a vertical line, you're good. And here, have this part just go off however you want. As long as it's a function, do anything you want there, and then our graph will still satisfy all of the conditions that we had. All right, well, that's it for our first video. Thank you for watching.